next speaker is Mariah White from Youngstown State University. She's also a rising senior, and she wants to go maybe into teaching. And her title is Mathematically Modeling Cardiac Myocytes.
Thank you all for coming. This past summer I took part in a research program at YSU. It was called EMBER, and it was an interdisciplinary project where I became an honorary biologist and was paired with another undergraduate biologist, and we worked with our faculty mentors, and we were modeling cardiac myocytes, which are heart cells. And the one particular disease we were studying was long QT syndrome. So long QT syndrome is characterized by an elongation of the QT interval of the heartbeat. What does that mean? If you have the ECG or EKG, they're looking at, you can look at your heartbeat, and this is the different, they did a very smart thing, did alphabetical, P, Q, R, S, T part of the heartbeat. And so between the Q and T part, it's elongated, which can lead to arrhythmias, which is irregular heartbeat, which can lead to death. Good. So when you have long QT syndrome, the disease we're studying, there are sex differences actually, which are kind of surprising. Adult females are more susceptible than adult males to long QT. But the reverse is true of children. So little boys are more susceptible than little girls. So there was some preliminary research done on the left ventricle by the biology advisor, Dr. Carl Sims, and they found one thing. They were looking at a particular part of the disease, which was the L-type calcium channels, the long-type calcium channels in the heart. And so they found that there were more L-type calcium channels in females in the left ventricle, which elongated the plateau phase, which if you look back here, this part elongated and led to EADs, which are pathological voltage changes. So they were using the Lewis-Rudy 2000 model, mathematical model, which we actually used for our research as well. And so here you can see when there was longer, more calcium, elongated the plateau phase, and the potassium channels were blocked, which brings the voltage back down, we got 8 EADs, which led to arrhythmia. So we were hypothesizing that there are sex and regional differences in the density of L-type calcium channels in the right ventricle. So that's what we were looking at this summer. So I actually got to do some biology, which was really very fun. And we actually isolated heart cells, which was the screen, my title screen, with a picture of heart cells on the microscope. We collected data using the patch clamp technique, and if you look here, we have our density. This is a calcium trace. The red is female, the blue is male. We found that there was indeed a higher density of L-type calcium channels, which would correlate to more L-type calcium channels in females, which would support our hypothesis. So that was really neat. But before I go into the mathematical model, mathematically modeling excitable cells all started with Hodgkin and Huxley back in the 1950s. So they took an electrical circuit and they were modeling actually neurons. They looked at the action potentials of a switch. And so what they started doing is they used Kirchhoff's law to saying that the sum of the currents through a circuit, sum of all these currents here would equal 0, where the current through the capacitor is equal to C, the change in voltage with respect to time. So we plug that in and we solve for dV dt. We see our voltage equation here. The Hodgkin-Huxley equations are actually a four-dimensional system, which consists of our voltage equation and gating variables equation. They actually take the form of using Ohm's law. And I want to look just at a representative sample here of the sodium current. So we have our sodium current, which has the form, the conductance, which comes from Ohm's law. And we have these gating variables here. And we have our reversal potential. Now the gating variable is a voltage dependent. And so basically we're trying to reach the gate is trying to reach its voltage dependent steady state at a rate determined by its time constant. So just some things to keep in mind as we go into the Lewis-Rudy model, which is much more complicated. So what about the Lewis-Rudy model? It's actually much bigger. Has a system of 12 differential equations has one voltage equation, 6 gaining variables, 3 calcium concentration equations, 1 sodium, and 1 potassium. There are a total of 15 outer currents, which are conveniently used in this diagram here, which is probably the best diagram in the world. Not all of them are based on Hodgkin-Huxley formalism, so not all of them have gaining variables. And something I will be going into a little bit later are these SR fluxes, which are in the sarcoplasmic reticulum here, which houses calcium. And so we have these 4 little fluxes there. So we keep track of calcium concentration, which is what we're looking at more because of long QT affected by calcium concentration. So we're looking at the 3 compartments here in the myoplasm, the junctional sarcoplasmic reticulum, and the network sarcoplasmic reticulum. So I'll actually go through that a little bit more. So if you think back to the Hodgkin-Huxley, we have a voltage equation which is similar, but much, much longer. You see, many more currents involved here. Just a representative example of one of the currents here is fast sodium current. So similar to the Hodgkin-Huxley, we have conductance and activation, but we have another gaining variable because we have the fast inactivation and the slow inactivation. So, like I said before, we have not all currents are defined using the Hodgkin-Huxley formalism. Some of them are exchangers and pumps. For example, we have the sodium-calcium exchanger, which not only brings sodium into the cell and calcium out, but it works both ways. So it doesn't exactly have Hodgkin-Huxley formalism. So, what about some of our concentration equations? Remember, we have 3 for calcium, 1 for sodium, and 1 for potassium. So, using, we can look at our diagram again here, but if I'm going to take a representative sample, I'm just going to look at the calcium concentration in the NSR, which would be right here. Oops. Let's go back. Sorry about that. So we have here, this is the sum of the currents of the uptake, which is the flux here, coming into the NSR, the leak current, which leaks out into the myoplasm, and the transient current. Here we actually had to do a lot of scaling, which was a lot of fun when it came to coding to figure this out, was you were dealing with the volumes between the JSR and the NSR. Here we actually have the calcium concentration in the myoplasm, and we have the, we had a little bit of scaling problems because we were trying to deal with currents and fluxes, which have different units. So we had to do some conversion factors and scaling as well. And a lot of stoichiometry, because between the sodium-calcium pump, there's every 3 sodium for every 1 calcium, so that took a little while to figure out. We actually were working on coding this for a while. We ended up using a C++ model, and all the graphs that we've done were using MATLAB. So let's actually look at some of the things that we did. Here we have the action potential that was actually generated by the model, which looks a lot like what was shown on our first screen there. One thing to notice here, we had to add the transient outward current, which kind of brings in this dip, which is Rudy was for guinea pigs, and we were using rabbits, and rabbits have this transient outward current, which is also a human. So we wanted to make it more humanly real.